So y equals -3 is my amplitude. So I have to go up to +3 down to -3. There is no phase shift here. None of these I put any phase shift in. So we're going to start at 0 degrees. This is going to be the start of that sine wave. What is the wavelength going to be here? 360. I put in theta instead of x, but we can still read it as 1 theta equals 360. Dividing by 1, it's 360. So our cycle will complete here at 360 for that one, which means the midpoint of the cycle is at 180. So that's our other equilibrium, is right there. Since this is a negative amplitude, that means it's upside down. So instead of at the 1/4 wave, the 90 degrees in this case, instead of having a peak there, we have a trough at -3. Then the 270, we do have the peak there instead of a trough at a +3. There's our wave. For number 2, y equals 2 sine 3 theta. Again, there's no phase shift, so this wave starts at 0. What's the wavelength? 120 is our wavelength because it's 3 theta. So 3 theta equals 360. You divide by 3, you get 120 is our wavelength. So the complete wave is done at 120. The midpoint here is at 60 degrees. So we'll be back at 0 or at equilibrium at 60 degrees. Halfway to there, the 1/4 point is a peak, amplitude of 2. So it goes up to 2 there. Our 3/4 point is a trough at -2. So there's our wave. Now I'm going to do another wavelength to kind of fill in, do another one yet to fill this out to 360. So there's what that would look like from 0 to 360 degrees. Or 0 to 2 pi if you want to do it in radians. Y equals 2 cosine theta. What's the phase shift? None, right? What's our wavelength? .360. So now, since there is no phase shift, we start at 0. But now, since this is a cosine wave, we start on a peak. So our amplitude is 2. We start at a peak of 2. 360-degree wavelength, which means at 360, we're at another peak of 2. So halfway is at 180. That's where we'd be at our trough of -2 right there. The quarter mark, we're at equilibrium. 3/4 mark, we're at equilibrium. That's a really ugly wave. Let's try that again. Not a lot prettier, but it gets the job done. So there's our wave. Any questions there? So the next one, y equals cosine 2 pi. No phase shift. What's our wavelength? 180. So the wave will end here. So our amplitude is 1. So at 0 degrees, we're at our peak of 1. At 180 degrees, we'll be at a peak of 1. At halfway, at 90 degrees, we'll be at a trough of -1. The quarter mark would be 45 degrees, will be equilibrium. Halfway between here would be the 3/4 mark, we'll be at equilibrium or 0. So there's that wave. I could keep going with it if I wanted to finish out 360 degrees or 2 pi radians if I wanted to. Any questions there? Okay. What's going on here? Okay, exactly. We're not used to seeing it written that way. Haven't really talked about this yet. But what this really is saying is y equals 2 times the sine theta over 2 is 1/2 times theta. So 1/2 theta equals 360. If we divide by 1/2 or multiply by 2, theta equals 720 degrees is our wavelength. So we start at 0, we'll end at 720. At what point, since this is a sine wave, at what point will we be at 0 again in between there? 360, the halfway point, yes. At what angle will our first peak be? 180, right? It'll be a peak of 2, 180 degrees. And then our first trough, which will be at -2 because it's an amplitude of 2, will be at 540. So it just gives us a really stretched out sine wave. What do you guys think? Not so bad? Okay. Today we're going to shift gears a little bit. Obviously, we're talking about AC current right now. AC current is that sine wave. And when we're dealing with AC current, we talked about amplitude of the wave and all that. The amplitude is what would be called our peak voltage peak. What you guys are used to calling 110 or 120 volt power, what comes out of most of your standard wall outlets, actually has a peak voltage of 170 volts. Now, we mentioned this a little bit Monday. There's voltage peak to peak. We do P-P for peak to peak. What would that be here? 340. Yeah, just double the peak voltage. The wavelength with what's coming out of your wall outlet, I'm going to do this here from the beginning of the sine cycle to the end of the sine cycle, is 1/60th of a second. We measure that in terms of frequency. The frequency would be what we call 60 hertz. So instead of having angles on our x-axis, instead of having 0 to 90 to 180 degrees or 0 to pi over 2 to pi radians, for the current, it's going to be time now, seconds, on that axis. The frequency being 60 hertz, wavelength being 1/60th of a second. So that's going to be sine of 60 x, 60 being that frequency. 170 volts is our peak, our amplitude. Now, your y-axis is still voltage, yes. So going this way is volts. Now, because we tend to measure in radians, rather than seconds, we talk about radian cycles. This ends up getting listed as 170 times the sine of 2 pi radians is a single cycle. So 2 pi times 60 times x. So it's 60 cycles per second is your frequency, but we want to look at it as radians per second rather than cycles per second. 2 pi is a single cycle. So 2 pi times 60 is your radians for your frequency. That should look familiar for those couple problems off your test. We often talk about equivalent DC voltage. Most of Ohm's laws originated on calculations from DC circuits. You know, the whole voltage equals current times resistance, V equals IR, is a DC voltage. In fact, the abbreviation V for voltage is a DC term. When we talk about AC current, we usually use what letter? E. E is for electromotive force, is what that stands for, EMF. Because in the AC current, that voltage is not a constant push. It follows that sine wave. But what usually gets put in there for the voltage is something called RMS voltage. RMS voltage is the equivalent DC voltage. For a particular peak AC voltage. RMS, by the way, stands for root mean square. It literally means the root of the mean of the squares. I'm going to show you what that means here. So we're going to list here angles. I'm going to do this in degrees just to make it easier on myself. Hopefully I'll recognize that pattern. 60. Let's see here. Let's do it. Do it a little bit smaller. Smaller increments. I'm actually going to stop at 345 instead of 360. So the sine of that angle equals okay, well, I want you to do this for me. I spell out the whole word apparently. Okay, so those are our angles. Or sorry, our sine. Let's graph this. So you can see that it actually is, there you go, a sine wave. RMS means the root of the mean of the square, which means you do the square first. So the square is going to be that number squared. So we square each of those values. The mean means you find the mean of those squared values. So it comes out to the 0.52 whatever. The root means then you take the square root of that mean, you get 0.72. Something's just a little bit off on that. Maybe I do have to go all the way to 360. Let's try that out. There we go. You do have to go all the way back to 360. So it's the root of the mean of the squares of the values. Notice we get a value there of 0.707107. We've seen that value before. Do you remember where? If I go to my calculator, 1 divided by the square root of 2. 0.707107. That RMS voltage goes off of the square root of 2. So if my peak, now this is a sine, just a sine wave here, you can see my peak is at 1, my RMS would be 0.7071. So it's that peak divided by the square root of 2. So RMS, root mean square, VRMS is equal to V peak divided by the square root of 2. Now, for those of you that are math purists, you'll know that having the square root of 2 on the bottom of the fraction is really bad form, but I don't care. That's what the actual calculator is. Yeah, so this is a 170 volt peak divided by the square root of 2. 120.2. That's where the 120 volts comes from. I'm not really sure where the term 110 came from. It really is, if you put a meter in the outlet, it really does give you an R. If you have the meter to the RMS, it's 120. Yeah. Yeah. I really don't know where the 110 came from, because it's never 110. Okay. So when we're dealing with Ohm's law, we are not dealing with, there is an instantaneous voltage and instantaneous current based on resistance. Now, resistance is constant. Resistance is not subject to the cycles of the sine wave of the AC current. But obviously the voltage and therefore the current itself would be subject to that. It'll cycle through. So when we do those calculations, we usually use VRRMS is equal to current RMS times resistance. So if we have a 170 volt peak voltage subject to a resistance of 40 ohms, what current would we expect to be flowing there? Well, RMS we found, of course, voltage RMS here, we just found to be 120.2 volts, right? So we're going to put in 120.2 volts equals IRMS times that 40. We take the 120.2 divided by 40, 3.005. Amps is my RMS current. That's my RMS current. Now, what if I wanted to know the peak current? Well, I have two options. I could go back to the square root of 2. I know that the RMS current is going to be the peak current divided by the square root of 2. So to solve for peak current, if I have the RMS current, I would just multiply by the square root of 2. Oops, now divide times. So I take that 0.3005 times square root of 2, 4.25 amps is my peak. Or I could have gone back to Ohm's law and just used the peak voltage. 170 voltage peak equals current times 40 ohms. Since this is my peak voltage, this is going to give me a peak current. 170 divided by 40 is going to give me 3.75. Not 3.75, 4.25. Come on. There we go. 4.25 amps for my peak. So Ohm's law works both for peak and RMS. You just have to make sure that if you have one value as a peak value, the other value is also a peak value. And the same the other way around. If one of them is an RMS, the other one has to be an RMS. What peak voltage is required through 20 ohms to supply an RMS current of 6 amps. I'm going to try that one in your notes. Give me a second. So we've got V equals IR. 6 is our current, 20 is our ohms. What voltage is this going to give us, peak or RMS? RMS, because the 6 amps is an RMS current. So that gives us RMS voltage of 120 volts. I really wasn't shooting for that, but it's convenient that it came out there. So then our peak voltage is going to be square root of 2 times the RMS of 120. Basically 170, 169.7. Not so bad. So if we can use Ohm's law on RMS, or we can use Ohm's law on peak, why do we care so much about RMS voltage? Well, because power is always from RMS, voltage and current. So if we have a peak voltage of 340 volts over a resistance of 30 ohms, and I want to find the power. I would have to find RMS values here. So the RMS voltage is going to be that peak voltage divided by the square root of 2. 240.4 volts. In most applications, you probably would just round it, by the way. Then we need to find our current. So what did I say for ohms here? It disappeared on me. Did I say 30? Okay. We need to find our current then. V equals IR. 240.4 volts equals I times 30 ohms. So I take the 240.4 divided by 30, which gives us 8.8 8.01 amps. Is that peak or RMS current? RMS, because that was an RMS voltage. So for our power, those are the values we're going to use. We have voltage, 240.4 volts times current, 8.01 amps. Giving us a power of 1925.6 watts, or 1.93 kilowatts approximately. What do you guys think? Not so bad? Okay. In your packet, it is page 367, 1 through 25, the odds. Let you guys have the last 15 minutes here to get started on those. Remember, tomorrow there is a quiz on